Good evening, everyone. It's March of 2020. Welcome to Combination Circuits, Lesson 2, Expanded Practice. I'm on my third device and my second document camera. I think we've almost fixed the zoom issues. We can't quite have me narrate along, but that's okay. I look like Night of the Living Dead anyway. So, love to everybody who's being homeschooled. Let's take a look at the combination circuits. First of all, if you didn't think this was a combination circuit, you're perfectly right. This is a regular parallel circuit. The point is to find this current here, you have to know something about the junctions. And you have to realize that as the total current comes out of the battery here, I1 splits off, and what's left is IT minus I1, and by conservation of charge, what goes out must come in. Alternatively, given that it then splits off into I2, I3, and I4, which join together, and join together, and join together, it's also clear that I2b over here is I2 plus I3 plus I4. And that's the kind of logic that you're going to need working problems with combination circuits. Pretty standard black box problem. 250 plus 50 equals 300. And now you've got a lovely parallel circuit with 6 volts out of a 2 battery pack, 100 ohms in this branch, 300 ohms in the next branch, and finding the total current should be very straightforward. Now this is the kind of problem we talked about in the previous examples. Again, black box, you got 150 ohms right here, and then you have the loveliest little parallel circuit. (150 ohms in one branch, another 150 ohms in the other branch. And it's very clear that both branches altogether are going to have a voltage drop of 6 volts. 6 volts on the way through here, 6 volts on the way through there, and then straight shot back to the battery. The question is, how many of those 6 volts are dropped in the case of the 100 ohm resistor? Is it possible to do this with a ratio? Yes, it is possible to do this with a ratio. If you're doing this with a ratio and you got the correct answer, rock on. More power to you. Keep going. If you don't know how to do this and you try to do it with a ratio, what is the likelihood that you will get it right? The likelihood, ladies and gentlemen, is 50%. Which one goes in the numerator? Which one goes in the denominator? If there's the slightest doubt, do it on paper. Branch current, whereby the current in this branch is the voltage drop over that 150 ohms, or you can do it by the total current. Look, 150 ohms, 150 ohms. Half's going left, half's going right. Either way, you'll get 0.04 amps, 40 milliamps. Then go back to the original picture. Check it out. One branch here, one branch here. If we want to find the voltage drop in the 100 ohm resistor, that's the current in the 100 ohm resistor, times the resistance of the 100 ohm resistor. Both of those numbers we now have. And that will tell you what the ratio would have told you, that 4 volts out of the 6 go into the larger resistor, being twice as large, and 2 volts out of the 6 are used to power the smaller resistor. 4 volts here, 2 volts there. If that's what your ratio told you, you are good to go. However, many people who are mucking around with ratios say, oh, this is a 1-to-2 ratio, so let's 4 and that one gets the 2. No. The bigger one gets the 4, the smaller one gets the 2. The circuit that's going to be a series circuit one of these days, it's just got parallel bits. You can see the parallel bits very, very clearly here. When we get to number 6, you're going to want to redraw number 6 just like this so you can see what is actually parallel. Draw it this way and you'll see the current of about 57 milliamps is going through all 3, including this black box. That means if you want to find the voltage drop of the black box, that's the current which you have times the resistance that you have, which is about 3.42 of the total 12 volts. Now, if you wanted the current going through this branch, That would be VB, which we now have, divided by RB, which we had from the start, which is going to be something on the order of 22.9 of the 57 milliamps, and it stands to reason that the other 34.2 milliamps are going through the top branch. You can do this. You can also do this. And this. It is a pity you're not in a classroom to hear the groans and the four-letter words that are usually shouted at this circuit. But if you make enough black boxes, you kind of get into the swing of things. You know, you get your game on, you get into the zone. Try doing this on Skype or Zoom with a couple of trusty pals so that you can sing the traditional whoa when you finally get the total current in this mother. Do number 5, finish number 5, draw your black boxes, find the total current, and you'll get the same answer as everybody else, namely, that if you black box this, you'll find that the total current is absolutely the same. And you might be tempted to say, there is no difference between these two circuits. The total current is exactly the same, only this one is cheaper, easier to wire, uses fewer resistors, so go with the cheap option. And that's the obvious theoretical answer from someone who's never actually had to build a circuit like this in their life. Pause, text your friends, get in a chat room, see what reasons might someone have to wire something this way, which is more finicky, twice as many resistors, and that means twice the expense. Press play when you've got a few ideas to share. If you've ever tried to wire up something like this in our lab, you will find that we do not have any 50 ohm resistors in our lab, which is going to mean making a circuit with a total resistance of 150 ohms is a real tall order. We have, however, a whole bag full of 100 ohm resistors. So one reason you might wire it this way is you're making do with what you have and you don't have to pay for custom parts. This is not at all an uncommon situation in the undergraduate laboratories across the world. You have equipment in the lab. You have till 6 p.m. to do what the professor has told you to do. Use what's there, make it work, and then you can go home. The more subtle answer, the more universally applicable answer to anything other than your lab TA and a 6 p.m. deadline is this. Remember why we don't ever wire anything in series circuits except for Christmas lights? Bad Christmas lights, broken Christmas lights, because what happens when one of them goes out? That's right, they all go out, and with a string of 1,000 lights in series, you can't tell which is the one that turned the other 999 off. Now look at what happens when one of these appliances is off, or one of these bulbs blows. Check it out. The current is still flowing. Now, not in this one, obviously, because it's broken, but that's how you know which one the broken one is, and you replace it. The other one, the one that's not the appliance, is usually called the shunt resistor. If you've got a shunt resistor wired in parallel with every single one of your appliances, it's not a true series circuit. It's a combination circuit, and that means you've solved the problem of what to do if one of them breaks or goes off. And that is a very powerful way you might want to wire something this way as opposed to the more simple and potentially cheaper way. This is one of the most telling problems in the Holt Physics textbook about combination circuits. The best, the most interesting, most realistic problems are problems with switches, where the whole circuit changes from one thing to another when you flip the switch. And this is a great example. Everything is laid out in right angles, the way textbooks like to do. It's an infinite network of resistors laid out in right angles. It's like freshman hazing for physics majors. Here's the switch. Switch is open now. That's good news. You know what open switch means? It means that wire isn't there at all. So redraw this circuit without that wire there at all and see if it looks any friendlier. There now. See a few obvious black boxes? All right, check the battery. Going this way, there's a junction. Going this way like the electrons, and there's a resistor. This, I'm sorry to say, is bound to be a series circuit with parallel bits. I know, it looks parallel, but Hit a resistor straight thing out of the battery. That would be series. All right. Box this. Box this. All right. We got 300 ohms here, 300 ohms there. That's not so bad. Now, here's a trick I strongly recommend. Right angles are good for printers. You know who they're not good for? Physics students. Don't let them boss you around like this. If you were on a lab bench, you would bend the wires so you could see what you were doing and the wires wouldn't be all that tangled up. You can bend the wires here too. Just like what you saw on question 5 and question 4. And now there's no question how those black boxes of 300s are arranged. We've got two 300s in parallel with each other. Redraw the circuit a third time. Complete your work. Find the total resistance in that last diagram. Find the total current. And then, if you're asked for the branch currents here and here, and you're asked for the local voltage drops here or here, then you'll have enough information that you need. Press play when you're ready to go. Now, redraw the circuit with the switch closed. You know what that means? It means you have to start the problem all over again. Switch problems are not one problem, they are two problems. One with the switch open, one with the switch closed. Draw all over again, and remember, bend those wires so you can see what you're doing, and if necessary, pinch them together so that parallel looks like parallel and not like series. The circuit, and boy is it a doozy. It's at this stage that people are typically very nervous because I haven't given you a battery voltage. That was just a typo. It was cut off in the diagram, but I'll stand by my typo. If the total current is V over 200 ohms or so, that's fine. My question is, how is it going to change here? First and foremost, bend these wires. You can see what's going on. So far, so good? This is still weirdness. Pinch these wires instead of bending them. There you go. Get rid of that. Get rid of that. Pinch them together until it looks a little more like this. Now, can you see where the black boxes are going to go? Now, you've got a black box here. Redraw that circuit. A black box here. This can be the same drawing. About 67 ohms here, about 67 ohms here, and when you're done with your new drawing, a little more like VT over 183 ohms instead of VT over 200. That is to say, smaller denominator, bigger current. That is to say, by flipping this switch, you flipped a setup from being series to being parallel. Parallel means more options, means more openings, means more opportunities for traffic to flow, and by golly, it did. The total current went up. On 7 and 8, just stretch this wire and pinch this together here, and you'll see the two 7s are sitting right next to each other in series. When in doubt, if you go through the first one, you have to go through the second one. Not true for this branch current. If you go through this 7, do not have to go through that 7. They are not in series with each other. What's more, that 7 is not in series with this 7. You can't have a series with a junction, with a T shape. So you're going to have these two in series, but not with the 7. Bend those wires. Bend those wires. You'll see that you've got a 7 and 14 in parallel, a grand total of 4.6, and a straight shot to the total current, this time with a given voltage of 12 volts. Follow the same pattern in dealing with number 8. You will need 1, 2, 3, 4, 5 diagrams in order to finish this. That's why I gave you the whole page. Mrs. Eliezer, I bet I can do this with only one diagram. Well, Purple Marker Boy of 2019 made that bet with me, and by golly, he got the total current with only one diagram, given that that diagram went from here to here and was almost completely covered in Purple Marker. However, I submit to you that if somebody asked Purple Marker Boy what the voltage drop was over here and whether he could put a 2-amp fuse at this point without the fuse blowing, the answer would have been, I don't know, but I got a great case of purple markers to sell you. So when in doubt, make the 5 diagrams. They'll be worth every inch of graphite.